Okay, to continue, as I've said, we are going to convert negative 100 degrees Celsius to 40, negative 40, because that is the available data that we have there, so that we can compute this refrigeration system. Then this is now the corresponding uh, value that we are going to compute. Okay, with with the same number that we have last a while ago. Okay, and this is the corresponding page diagram. I consider this evaporator temperature as negative 40 and 40 your condenser temperature or condensing temperature. To determine this, all you have to do is to follow the formula. Pressure corresponds to your 40 degrees Celsius and pressure corresponds to negative 40 degrees Celsius. Now you have your value of your PCAS. Okay, and this one we have there 87 B equal to H8 equal to HF at P cascade. Okay, your H5 equal to H6 at 8F 40 degrees Celsius. One of course is equal to Hg at negative 40, and of course H3 is equal to Hg at the corresponding cascade pressure. 2 and 4 are taken by using your chart. Okay, and then we can easily compute for the mass of refrigerant flowing in your low pressure loop. Okay, this is your low pressure loop, this is your high pressure loop. The mass flowing here, we can call that mrep. mrep and after point 3, the mass that is flowing into your high pressure loop uh, system is considered your total mass. We are going to compute this later on. Okay, for your mrep, for your mrep, you can compute that by usual computation of 3.5167 kilojoules second ton. Multiply that by the RE or the tons, the given tons, which is 100 tons over RE, no, refrigerating effect coming from the low pressure loop. Your RE, low pressure loop, is just equal to H1 minus HF. This one, H1 minus HF, H1 minus H8. So you can have values there in kilogram per seconds. Now you can now compute for the heat absorbed here. No? You have your QA coming from the low pressure loop. Your QA low pressure loop is just equal to mass rep multiplied by RE, low pressure loop. You have their kilowatt. Okay, and then again, you can now compute the power pressure A as well as the volume flow rate there. For power compressor A, is just equal to mass rep, that is the mass of refrigerant flowing in your low pressure loop, that is in kilogram per seconds, multiply that by the work of compression, WCA, wherein WC at compressor A is just equal to H2 minus H1. Okay, so that you have also that kilowatt. Your volume flow rate, BFA, the one that is uh, passing to your point 1, the suction point, is just equal to mass rep in kilogram per seconds, multiply that by specific volume 1. Specific volume 1 is the line passing to point 1, this one, have there B1. But since it is lying along saturated line, you can find this value in your table, wherein B1 is equal to Bg at the corresponding negative 40 degrees Celsius. Okay, so B1 is equal to Bg at negative 40 degrees Celsius. You can have their liter per minute, per minute. This is in liter per kilogram. Okay, liter per kilogram. Liter per minute or liter per seconds or per hour. Okay, in your BFA. Okay, after computing BFA and power compressor, then we can now compute the mass total, or the mass circulating into your upper loop by applying mass and energy balance into your cascade condenser. Okay, this one. To determine the value of your MT, or the mass circulating into your upper loop system, then apply mass and energy balance in the cascade condenser. Okay, so isolate the cascade condenser, this one. Okay. Then apply energy in, energy out. Okay, so this is considered 0.3. This is considered 0.2. This one is 0.7. Okay, and this one is 0.6. Now the refrigerant at 0.3 is considered your empty, as well as in your 0.6 empty. Now the refrigerant at 0.7 is considered MREP, as well as this one. And then at each point we have, of course, enthalpy, such as this: enthalpy 6, enthalpy 7, enthalpy 2, then enthalpy 3. Okay, then apply mass energy balance. Okay, energy in equals energy out, considering this. Okay, the energy going into the system is empty. This one, enthalpy 6 plus mrep, enthalpy 2. Going out is empty, H3, and mrep, H7. So you define empty. Transpose this to the left side. We have 0.6, then factor out empty minus H3. Then you have your mrep here, this one, that is H7. You transpose this to the other side. We have minus H2. So that we have empty is equal to mrep H7 H2 all over H6 minus H3. Okay. Do I have the right manipulation? Again, empty M6 going in this, as well as mrep H2 going in, empty H3 is going out, as well as mrep 7 going out. Okay, so we have it here with empty 6, transpose this to the other side, 3, mref we have H7, transpose this to the other side, we have H2. We have now mref H7 minus H2, H6. Okay, here we have your kilogram per seconds. So that is the refrigerant flowing in your upper loop, this one. So since we have already the empty, the mass total, circulating in your upper loop system, then you can compute for this PB, as well as the volumetric flow rate at compressor B. Your PB now is equal to the mass entering to your compressor B, multiply that by work of compressor B. Your work of compressor B is simply equal to 4 minus 3. H4 minus H3, H4 minus H3. Upon there, you have your kilowatt, and the volume flow rate at point B, entering your point B. Point 3 is still lying on the saturated line. So we have the line passes to point 3, specific volume 3 is equal to Vg at the corresponding P cascade. You can also use your table since it is saturated. Okay, so that we have empty in kilogram per seconds. Multiply that by specific volume at point 3 in liters per kilogram. So you can cancel that. You have your liters per seconds. Liter per seconds, or want it convert that into liters per meter, convert that. Then after computing PB, you can now compute for your QR. Your QR is simply equal to mass total multiplied by energy rejected. Here, your energy rejected is simply the difference of your enthalpy at 0.4 minus 5. H4 minus H5. Okay, so we have there also kilowatts. Then you apply system balancing. Consider the whole system. Apply energy in, energy out, considering the whole system. So we have only this. The energy going into the system is simply QA low pressure loop plus the compressor A plus compressor B must be equal to your QR. So that is the balancing. Okay, you can now compute your activity 13. We are going to use ammonia here, ammonia, NH3. The refrigerant that you are going to use in the system is HS3. Okay, try to balance this, and then next is the application with a different system and a combination of intercooler connected in the system as well. Okay, so activity 30. Next is activity 14. I will send it to you by picture later.